What happens if we have the complex number z equal 1 plus I and we successively raise it to powers z squared, which is 1 plus I times 1 plus I. After expanding out, we get 2I, z cubed, which is z squared times z, which you get 2I from the previous part, and times 1 plus I. And after expanding it, we get minus 2 plus 2I. Z4 is just z squared times z squared, so we got 2I times 2I, and we get minus 4. Now, let's plot all these 4 points on the Argand diagram. Once again, the horizontal part is our real axis, and the vertical part is the imaginary axis. So, where is 1 plus I? Somewhere here. In this case, z equal to 1 plus I. Where is 2I? Somewhere here. Z cubed, which is minus 2 plus 2I. Somewhere here. And z to the power of 4, which is just minus 4. Is somewhere here. If we were to actually find the displacement vectors of these complex numbers from the origin, we see a trend happening. We see that as we successively raise a complex number to a power, which in this case is just the complex number multiplying itself, we see that the displacement of the complex number from the origin gets wider, gets longer. Not only that, but we see an anti-clockwise rotation. So this gives a very geometric meaning towards complex number multiplication, in the sense that whenever we multiply, the displacement vector gets longer, and the angle at which the complex number makes with the real axis rotates anti-clockwise. So this kind of leads us to the idea that we should do complex numbers in a much better way. Instead of just z equal x plus iy, which is only just vertical and horizontal movement, we should somehow make these complex numbers in a more rotary form. And we can do that by transcribing our complex numbers into something called the polar axis. Now, if we get a complex number again, z equal to 1 plus I, we can take this complex number and we can extract a very rotary form out of it. Now, this right angle triangle here, let's just zoom in on it, is one up from the horizontal axis and one away from the origin. So in other words, this hypotenuse is going to be root 2 by Pythagoras' theorem. Not only that, but we need an angle here. An angle here. So, and this angle would be tangent theta is going to be equal to 1 on 1, opposite over adjacent. So that angle there in radians is going to be so we can change this complex number z equal to 1 plus I into an equivalent form of what they call the trigonometric form, where it is root 2 times cosine pi on 4 plus I sine pi on 4. We call this the trigonometric form of a complex number, often abbreviated to root 2 cis, which simply just means cosine I sine pi on 4. With this, we can actually express a whole multitude of properties from complex numbers thus open up for us, inclusive of the rotary effect of multiplication, and later on we're going to see division. And because we have defined now the angle between the complex number and the real axis, we can define something called the argument of the complex number, which is just the angle, and we can see the properties of the absolute value of the complex number, the distance from the origin, and we can see the properties of the arguments, the angles from the origin. Before we carry on any further, we would like to define how complex numbers multiply and divide in this so-called polar form or the trigonometric form. Previously, we took the same complex number z and we successfully multiplied it by itself. In other words, we powered it up. So let's take two complex numbers which are not necessarily the same. Let's say z is equal to r1 radius 1 cis theta, and w is equal to r2 cis phi. So what is z times w? I'll write it out in full. Firstly, we'll just r1 cis theta multiplied by r2 cis phi. Because r1 and r2 have to be positive numbers because they're just the radius from the origin of that complex number, so we can just factor out the real numbers. I'll write all the cosine and I signs out in full. Cosine theta times cosine phi. Cosine theta times I sine phi. I'm going to write C for cosine and S for sine. I sine theta times cosine phi and I sine theta times I sine phi. Let's group all the real parts and imaginary parts together. Cosine theta cosine phi is real, minus sine theta sine phi is also real. So we get cos theta cos phi minus sine theta sine phi. Plus, let's do all the imaginary parts. Cosine theta sine phi cos theta are going to be imaginary. Oops, I just write the same thing. There we go. And what is this? This is the sine, this is the cosine addition formula. And what is sine theta cosine phi, cosine theta sine phi? This is the sine addition formula. So what we see is that when we multiply two complex numbers which are not necessarily the same, their radii multiply, therefore the vector elongates, and the angles simply add up. So what if we have the complex numbers, the ratio of the complex numbers with each other? We get r1 cis theta on r2 cis phi. Writing out in full, we're going to get r1 on r2, since they're just numbers, let's put them outside, and we're going to get cosine theta but you know that we can never divide by a complex number, we must always multiply by the conjugate. And so get using this guy, right? Cos theta times cos phi. Cos theta minus I sine phi. I sine theta cos phi. And I sine theta, I sine phi is going to be plus sine theta sine phi. And a complex number times its conjugate, it must be a real number. Cos phi times cos phi is cos square phi. So we get the cross terms cancelling off, and we get cos square plus sine square, which is 1. And upstairs we're going to get the real parts, which is cos plus sine, which is the double angle identity of cosine, what the subtraction. And we get cosine, sine cos. And the imaginary parts are going to be the double angle formula for sine. There, over here we got both the multiplication and the division of complex numbers expressed in trigonometric form.